Okay, I think we can probably go ahead and get started with announcements, and we can let whoever else joins in as we do announcements. The only thing that I wanted to let everyone know is that we are being recorded. Um, Also, the link to receive AIA credits is in the chat, so please click on that and fill out the Google form. And also, I wanted to remind everyone that our next program will be January 17th, and this is part of our um, Design for series. And so this one is Design for Ecosystems. So please join us for that. And that is on the BSA website now. So you can go ahead and sign up at your leisure. And then I'll let our presenters take it from there.
All right, thank you, Beth. Today's presentation will be a three-part presentation. I'm Patrick Murphy. I'm the Director of Sustainable Design at Vanderbilt Engineers. I'll be introducing the way that the AIA framework for design excellence approaches energy. And then we have both John Hyde and Heather Walters to present how they have applied the design framework for design excellence into their work, particularly with a focus on energy and carbon. And they'll take it a step further than just operational. They'll also consider embodied carbon. So allow me to share the screen. Just a second, please. Am I sharing? Are you seeing? I have three different versions of PowerPoint on my screen right now. Are you seeing the full screen version? Are you seeing the presenter view, or are you seeing something else?
It looks like the full screen, not presenter.
Okay, great. So our agenda today, like I described, will be to go through the energy principle within the AIA framework and illustrate that through case studies. We'll take, roughly speaking, about an hour from now until about 7 p.m. going through the presentation content. You're welcome to put questions within the chat during the presentations. And then we'll have a healthy amount of time after the presentations conclude around 7 for an open questions open forum.
Patrick, just real quick, I think the view we're seeing is like it's like the PowerPoint interface, so I can still see like the top view.
Okay, let me switch what I am sharing. How about that?
Still see the same thing. Oh, there we go. Perfect.
Okay, great. Thank you for catching me. All right. So the learning objectives, which you saw on the website when you registered, we want to, highlight that the AIA framework it is a toolkit for you all to use in your work to give you tools to work through in the design process to optimize not only for energy, but all of the other categories that the BSA Committee on the Environment is highlighting in their Designing For series. The toolkit for each category includes prompts for the design team to think about or to question their approach to the design, areas to focus on. They really distill it down to like understanding that we could spend hours or even weeks talking about any one category, but if you could only do a couple of things, what's the most impactful use of your energy and your time, along with best practices and a list of resources. And then for those of you that are familiar, especially if you have submitted a project for an AIA award, the AIA has what they call the super spreadsheet, which includes a lot of metrics to track and compare projects against one another. And we'll go through some of that later in the presentation. So you'll see what metrics are being tracked by the AIA for these projects. Focusing on energy, zooming way out. So I don't think it's surprising to anyone on this call that the amount of energy used per person is predominantly higher in Western and industrialized countries. But as we're seeing development in other parts of the world, the energy use is increasing pretty rapidly on a per capita basis in those areas as well. And one of the things that we've observed over the last decade, maybe a little bit longer, has been this transition from energy focus to energy savings, energy cost savings, to more of an emissions focus. And one of the ways that we've kind of illustrated that shift has been the series of UN meetings that have occurred, and the latest of which just concluded earlier this week, COP28 in Dubai. So you're probably familiar or have heard of the Paris Climate Accords back in 2015. And at the time, that was the accord that established a global limit or goal on limiting global temperature rise to 1.5 degrees Celsius. But what was left unsaid in that commitment was really how we were going to get there. And one of the biggest things that happened just this week, if you haven't seen in the news in the last 48 hours, has been that this COP has come out with an agreement, a worldwide agreement, to begin the phase out of fossil fuels. This is being called basically the beginning of the end for fossil fuels. Now, we could talk for hours about some of the nuances with this and some of the weasel words within this that get, commitment countries that have committed out of actually moving away from fossil fuels. But this one section out of it is a many-page document, but this one section that I have on the screen now is the most relevant for us and our work and what we're going to see here in the next, several years of our work. So the international commitment is to triple renewable energy capacity globally. It is to accelerate efforts towards net zero emission energy systems through transitioning away from fossil fuels. That statement, transitioning away from fossil fuels, out of the dozens of pages in this document, is a new international commitment, which is really fundamental for our work and for the global approach to decarbonizing. Additionally, accelerating and substantially reducing non-carbon dioxide emissions. So think, it's not just about carbon in the environment, but also, for example, methane, which is basically the primary ingredient of natural gas. When it leaks into the atmosphere through leaky distribution systems or at the site of extraction, that has a greater impact on global warming. Also, refrigerants that are used in mechanical systems, they're not necessarily CO2 emissions, but they have an equivalent CO2 emission because of their effect on global warming. And then one of the last ones is phasing out inefficient fossil fuel subsidies. So we're even starting to see this here in Massachusetts and a number of other states where utilities had basically used incentive programs over the last 10, 15, 20 years that focused on energy efficiency or reducing energy. Now we're starting to see those incentive programs basically completely eliminate the use of fossil fuels, even efficiently, as something that is eligible for incentives. So, I think we here in Massachusetts are already seeing a lot of this on the forefront, but what now we are seeing is this global commitment, and this was very, very big news in the the climate advocacy world in the last couple of days. So, bridging that into the AIA framework, the focus on energy that the AIA framework provides lists these categories as things to focus on in your design. What's highlighted in green is aligned with this new language that comes out of COP28. But the general approach here is, what I certainly spend, and I know John and Heather, when we're working with you all on projects, spending time focusing everyone's efforts to be the most efficient at reducing energy and decarbonizing. And that starts with passive design strategies, benchmarking and showing progress relative to those benchmarks and relative to goals that you set. working on eliminating fossil fuels as much as possible through electrification, utilizing energy modeling to inform design decisions, commissioning the project when it is completing construction to make sure it operates as the design team intends, targeting ultimately, especially for those of you that are at AIA 2030 commitment firms, net zero energy, net zero carbon. And for those of you that are, keeping tabs on LEED and LEED version 5 and have participated in Green Build, are seeing this bigger shift towards building grid integration, which basically is focusing on as these renewables come onto the grid, and the time that they're generated versus the time the energy is consumed. We want our buildings to interact with the grid in an intelligent way to really make the most of all this new investment in infrastructure. The toolkit provides a number of prompts for design teams to consider as they go through the design process, especially at the very beginning. How can passive design strategies contribute to the performance of the project? How can the project exceed code efficiency standards and move towards net zero? I think we all should look at code as an absolute minimum and to strive to do better, with the goal ultimately being net zero energy, net zero carbon. How can the project be powered by clean and renewable energy sources that could be both on-site and off-site as the grid utilizes more off-site renewable energy generation? And also, can the project provide for continuous performance improvements over its lifetime? So let's say, no matter how efficient or sustainable your design is now, the world that these projects will inhabit over the next 20, 50 years will inherently be different. And how are our designs teeing that building up to succeed in that future world and not be kind of beholden to the way we did things in the past? The framework tries to whittle many pages of approach that I won't get into here into 4 categories. These 4 categories are kind of a common thread through a lot of the different framework categories, but the first is designing for zero carbon by reducing energy use and utilizing that benchmarking process, goal setting, and iterative energy modeling to inform design. Designing for resilience, that can especially be for all electric designs that are designed to work with the grid as the grid adapts to this transition over these next 10, 20 years. Equitable design. So here, this is tied to resilience through designing for passive survivability. This means, when there's a loss of power, that the building can continue operations or minimize the impact on the occupants. And all of this is important to keep in mind, that especially for owners and for the residents of these projects that are lower income, that we're not leaving them stranded with ever increasing costs of fossil fuel based infrastructure and not incentivizing or supporting them making this transition. And then also not leaving them stranded when there's, say, a weather event or something that causes a loss of power, that our designs are equitably allowing them to, maintain safe and healthy operations during those events, just like any other project would. And then lastly is designing for health. So one of the side benefits of the electrification movement is that by eliminating that combustion, especially indoor combustion, we're helping create healthier indoor environments. I know, for example, just this past year, I switched my kitchen from a gas range to an induction range, and the indoor air quality I could already perceive the improvement. I used to be able to smell gas when I was cooking, and now I have a healthier environment. Lastly, so the super spreadsheet, and this is what, again, you're familiar with if you've ever submitted a project for an AIA Design Award. Within the energy tab of that spreadsheet, it provides the metrics that are trying to be measured and reported and used to compare projects head to head. At the first step is benchmarking. This could be through the AIA, the Zero tool, or other metrics that we use to benchmark our projects, both from an energy use intensity perspective, but also a CO2 emissions perspective. There's a table that provides inputs for your predicted energy use. This is what's going to come out of your energy model. And then also your measured energy use. So we want to basically bridge between the design team intent and actual operation. And a lot of the trends in submissions for AI awards, for example, really want to see those measured, real world proof of performance and not just design team intent. Then that goes on to provide outputs in terms of energy use intensity, CO2 emissions, annual operating costs, comparing the predicted versus the measured. How well did the team try and make sure that those two values are as close together as possible? For projects that are maybe smaller in scope or don't have as much of an influence on, say, building envelope or MEP systems, they're also tracking lighting power density as a key metric to document progress on reducing energy consumption within the scope that you have for a project. You're familiar with this if you've ever done a submission for the AIA 2030. If your project has energy model data, you want to report total energy use. If it's an interiors project, you may only be able to provide a lighting power density. And then lastly, and certainly as an engineer who's worked with a lot of different architects, the focus on window to wall ratio is a really important one. While we certainly want to increase the amount of daylight and views, we need to be cognizant that glass is inherently a poor insulator for buildings. And so we need to find the correct ratio of window and insulated wall area for our project on each facade. These all glass buildings are probably going to be obsolete, and the designs we see in the future will rely on more strategic deployments of window area. And so that's one of the metrics that's being tracked in the framework in the super spreadsheet. So with all of that to tee us up, let me stop sharing. And I will hand it off. John, I believe you were going to go first. Is that right?
I think Heather was going to. Yeah,
Heather
she was
is. All right.
I think I'm going to go first. Yep.
Great. So Heather, hopefully you were able to share the screen and take it from here.
Can everyone see my screen?
Let's go.
The most boring way to start a presentation. So thanks everyone. Today, I'm going to be talking about the box when we're designing for energy and whole life carbon. So the intersection of operational and embodied carbon. So I'm in Thornton Thomas Studies sustainability practice. We really have a focus around climate action in all of what we do. And the intersection of operational and embodied carbon in our buildings is really one of our focus areas, something we really care deeply about. And part of that is because when we're looking at emissions in new construction over a lifetime of a building, we understand that operational carbon at the end of a building's life traditionally is a much higher part of the building's whole life carbon story than embodied carbon. But if we're thinking about the time value of carbon and the importance of carbon that's hitting our environment now and impacting our climate today, we really need to be looking at the nearer term, like the first 10 years or so of a building's life. And if we look at that part of a building's life, 70% or so of that carbon story in the first decade of a building's life is related to the embodied carbon, when a much lower percent is related to operational carbon. And as we continue to make our buildings more and more energy efficient, that number is going to continue to trend towards higher embodied carbon percentage in this first piece of a building. So that's why we think it's really important to consider these two pieces together and not separate. So when we talk about this, we talk about whole life carbon in buildings. we look at a traditional green building approach from an energy reduction standpoint. And a lot of times what we're looking at, say in 2018, was a single point in time energy model. We're able to identify things we could do to reduce our energy use at this point in a building's life. And so we use less energy year on year, and that's all great, but this is the past. The future, we really think, is about thinking about a building's whole life carbon story. And this talks about a lot of the things that Patrick was talking about. How do we design our buildings to be supportive of a future that is decarbonizing globally? So we're looking at reduction of the embodied carbon, both at the beginning of a lifespan, and then how can a building continue to respond to a changing environment and a changing grid as we go forward. And really, how can we get to this flat line, prepare for a net zero grid? And there are lots of things, you can do, right, to kind of impact these buildings on each part of its life cycle, from utilizing efficient embodied carbon structural systems and facade materials, really good mechanical systems that are going to lower the speed that line goes up, on-site generation of PV, understanding and designing for retrofit is really important, and then making sure our buildings are grid adaptive so we can make the most use of renewables at the end of a building's life. So we really think, as we're thinking about this whole life carbon, we think we're at the beginning, and we think as we go forward, we're not going to be talking about designing for energy as much as we're going to be talking about designing for carbon reduction. And that's whole building life cycle carbon reduction with a focus on the first 10 years or so of a building's life. So as I kind of explain this concept, I like using kind of this framework, right? So if we're looking at a line and we're carbon CO2 equivalency is on the side, as time goes on, CO2 emitted by a building goes up. Day one, we're not starting at the bottom because that's the embodied carbon in our building, right? So we kind of understand this kind of year-on-year progression in a building's life cycle. Embodied carbon at the end, at the beginning, operational carbon up and up, whole life carbon at the end. So we understand, I think, intuitively that a lot of times less is more, right? Less insulation, less good systems, less care about what's going into our buildings day one means at the end of the day, we're going to have more carbon. That's bad, right? We don't want less to be more. But at the same time, a lot of times we overshoot, right? We're making super aggressive decisions. We're trying to make the best, most efficient systems and buildings without thinking critically about the decisions we're making along the way. We're putting in more insulation, super sophisticated systems, really complicated interiors, all of these things, and more day one carbon still ends up with more end of life carbon than if we had done a baseline building. Our goal is to make those choices intelligently and considerately, so more day one carbon ends up as less embodied carbon. So we've optimized those numbers, and we'll talk about some options of that. Or even better, if we hit the sweet spot where we can find a place where we focus on passive design strategies and simple, effective systems and strategies like natural ventilation, where less day one carbon can also be less end of life carbon. And that's really the sweet spot, when less can be less. And it depends on a lot of things, right? It depends on your building typology. A school's going to have different questions and answers than a lab building. The climate your project is in is going to matter. Are you building this in Boston or are you building this in Florida? That's going to change the questions you're asking as you're trying to track this line and the answers you're going to get. Regional availability of materials is also going to impact this, right? Are you in Boston where triple pane windows are not unusual? Are you in a place in the country where your contractor is going to look at you like you have, two heads if you tell them that you're going to put triple pane windows in this school? And your grid matters too, right? How renewable is our grid? What are we looking for? So all these things come together when we're asking these questions. So that kind of is just a base work. I want to talk briefly about facade considerations and whole life carbon. So we understand that reducing load is really our first important step, right? We reduce the load, we electrify the building. We reduce the load more, we're a better building, more energy efficient. We reduce the load more. This is all great, but if we're reducing the load by piling a ton of embodied carbon on top of this, you know, this pyramid might fall. And now we haven't ended up with that goal at the end. So when we think about facades, we want to think about what they're for, right? They do a lot of things in our buildings. They protect us from the environment. They make the buildings look visually attractive and make them a thing that communities want to keep and save. They offer comfort to building users, and they help reduce that energy demand we were talking about. But good facade design has both carbon benefits and carbon costs, and we need to be considering those holistically as we're looking at building designs. A lot of effort and research and thought and studies have gone into helping us understand how we can reduce our operational carbon in facades, but there hasn't been as much effort in this embodied carbon side, and how do we start to optimize this? So it's really important that we compare options, and we're getting to the place where we can do that relatively simply. So here's a project that we worked on in London. We had several different wall assembly types, and the question was, does it make sense to add how much insulation? Number one, mineral wool, how much mineral wool insulation? And then does it make sense to add additional interior insulation to this wall assembly? And at the end of the day, by doing a really simple analysis of like a segment of the wall, right? This wasn't a whole building analysis, right? We were able to determine that by adding this extra layer of insulation, we increased our building embodied carbon by 3%. That's a lot. And we had the most nominal impact on the operational efficiency of this building. It didn't make sense to go to option 3. It definitely made sense to go to 4-5 inches of insulation. That was a good decision, but to go and add an extra layer on the inside just didn't pay off. And we can also have a similar discussion when we're thinking about triple pane windows, where we have an option anymore if we're going to do it. There costs and benefits, right? We understand that a double pane system has a lower facade cost, has a lower embodied carbon. That's great, but the thermal performance is worse, the energy demand is worse, and the MEP cost and MEP embodied carbon goes up by having the need for perimeter heating in these buildings. Whereas if we're looking at a triple pane system, our thermal performance goes down, our energy demand reduces, our MEP cost and embodied carbon goes down. The facade cost goes up and the embodied carbon goes up. Glazing is a pretty high embodied carbon item. And does it make sense to do this? It really depends, right? It depends on your climate. It depends on the project typology. It depends on a lot of things. In a really temperate climate, there may not be a carbon payback to go to triple glazing. But in a more aggressive climate like Boston, often we see there is, a real benefit, which I think this group understands. But if you don't do the study for your specific building and your specific location, you don't know the answer to the question. So that's what we advocate, asking the questions and getting the answers. And we understand that not all insulations are the same. Some insulations have higher embodied carbon and some have lower embodied carbon. And this is really important. So this is a really simple study we did for a middle school in outside Boston. And we were a couple of years ago, and we were looking at just a regular energy optimization study, trying to figure out the R value, or I'm sorry, the EUI of this school based on different R values of insulation. So we went ahead and we did this study, and we were able to give suggestions. But then the question is, was that really the right carbon solution if we're looking at the whole life carbon of the building? So we took a step back and we're like, okay, let's take a look at this. So this is the same type of chart that we looked at before. We're starting kind of up from 0 on each one of these lines. That's the embodied carbon related just to the insulation assembly of the building. So R15 is going to be the lowest because that's, the least. And then R40 is going to be the highest. So we kind of look at the operational carbon then lines year on year related to each one of these options. And you can kind of track out where that carbon payback is going to be for polyiso insulation for different carbon options, right? And this is a really easy study to do. This is something that you can do using EC3, energy model results, right? Pull quantities from your Revit model for the insulation you have, multiply that up. It's a really easy spreadsheet study that any project can do to really understand the carbon impact of these types of decisions in their project. We looked at polyiso. The payback's around 12 to 15 years, a little further. That's fine for a school. If we look at the mineral wool, which is, more likely the insulation we're going to use, right, in this type of assembly and system, we're showing a payback of 5 or less years, which really just demonstrates that the higher R value makes a lot of sense in the walls in a school like this. This makes sense. This is what we're seeing in new code requirements in Massachusetts. But if we look at the roof and we do the same study, we see those lines never cross, right? We don't see a payback for increased insulation in the roof, even at 60 years. And again, this is dependent upon the building geometry, the building typology, the location, lots of different things. But by doing the study, you're able to understand what those are. This is a really simple type of thing that anyone can do. Optimizing the form is also really important. And if you're looking at a little more sophisticated type study, you have the ability to use parametric analysis to start to understand your building assembly. And in this case, we looked at orientation, window, width, height, mullion depth. We looked at the embodied carbon of the elements, the operational carbon of the elements, the SDA, so the daylighting. And by doing this type of parametric study, we're able to start to optimize and figure out where that sweet spot is between energy use, occupant comfort, and embodied carbon, right? So this is a type of study you can look to for more sophisticated clients, more advanced projects, whereas the other study is something that you can have an intern work on in the summer and give you really good useful answers, right? So there's a huge range of studies that can be run, questions that can be answered, answers that we have the ability now to understand. So if we're going to talk about MEP considerations and whole life carbon, this is kind of the next piece of this. This is a study that we presented at Greenbuild a few years ago. And the question really is, what about the embodied carbon in MEP systems? Now, I will say that embodied carbon in MEP systems is very much the dark arts. We're still trying to figure it out. We're still making lots of assumptions and guessing. We're getting better and better, but it's still very preliminary. So take the numbers with a grain of salt, I think, but the concept is useful. And if you have a project who wants to be on the cutting edge of carbon work, understanding the carbon in MEP systems is, I think, really where it's at. So in this case, as we're looking at this building and we see this red line that will benchmark the next page, we see that a really basic boiler system has the lowest embodied carbon, right? And then we have air source heat pumps kind of on the higher end, and BRF kind of over there too. But if we look at the operational versus embodied carbon of these systems, we can see that now all of a sudden, because we've added this carbon from the energy use of the building to this, all of a sudden, the air source heat pumps, which were one of the highest before, are now one of the lowest, right? Or the lowest. And a lot of times people ask about refrigerant leakage in these systems and are worried about both VRF and air source heat pumps, kind of for the concern of refrigerant leakage. As Patrick mentioned, it is a big deal. But you can see that equivalent, emissions equivalent, doesn't make up for the reduction in operational energy, right? It's still the right decision. And when you see the low, medium, high, those are considerations of understanding of the data, right? And based on the data we have, you know, where do we assume the buildings are? So it's going to be somewhere in the middle here, but that kind of demonstrates. And you can see the line that was here up here, right, at the beginning, you know, is way down here. So operational is still the bigger piece for most of these systems. This is a really fun study that we did for a project in Boston, and very, very hypothetical lab building and air source heat pumps. And we looked at what if we 100% delivered capacity for this building with air source heat pumps. So going from a 94% fossil fuel free building with heat pumps to going to 100% fossil free building with heat pumps meant that because we had to hit those peaking, even though it's only for a few hours, the amount's so much higher and the heat pump efficiency goes down so much, we had to go from 30 heat pumps to 160 heat pumps. It's a lot. And then as we look at how those lines go up, operational versus embodied, again, same as we looked at before, we see that those lines never cross in that scenario in the anticipated lifespan of the heat pumps. So the question then becomes, what is that sweet spot in heat pump capacity for buildings? And that's really something I think that we're struggling as an industry to understand and make sure we get right. We don't want to overshoot the mark, but we don't want to undershoot the mark too, either. And then we want to talk about the elephants in our cities. This is an AI generated image. Isn't it so cool what you can do anymore? But anyway, so the elephants in our cities are our existing buildings, right? So it's really important that we talk about when we're looking at a project that we consider the 4 R's: retrofit, rehabilitation, renovation, and recladding before we talk about replacement. And here's just a couple really quick examples of this. So here's a study we did for a project that was considering a passive house certification for an existing university building in a mid-Atlantic climate, a confidential project. And we looked at a series of different opportunities to reduce our heating load in the project. And you know, the client's goal was passive house. At the end of the day, the lowest whole life carbon option was actually not the passive house option. It was just one step up. By doing the study, by taking a look at the operational and embodied carbon, in this case, the embodied carbon was divided against the anticipated lifespan of the building year on year. That's not something that we recommend doing anymore, but that's what when we did the study a couple of years ago, how it was. The total lifespan, the best embodied carbon, operational carbon story for this project was not the maximum upgrades. So I think that's a really good story and something to consider and think about as we're doing projects. And here's another example of a building. of a study we did for an existing building in Cambridge. Again, you know, the unrenovated building starts at 0 embodied carbon because we are not doing anything to it. We are not adding embodied carbon to that. And obviously its energy use is not very good. It goes up very fast. The renovated building has some significant embodied carbon for adding insulation. We filled the studs with mineral wool. We did some window replacement with thermally broken frames. Obviously, we did hydrothermal analysis to make sure we weren't going to break the building by adding the insulation to it. So we have a much lower embodied carbon. And we were able to show that the renovated building, you know, has a carbon payback of 2 years. Obviously, we know it's going to perform better. It's not a surprise. The interesting thing was that if we look at the replacement building, the carbon payback was not till 11 years. So that's significant for a couple reasons. That was based on the school's current campus systems. And if you look at these institutions which are electrifying, you start to see and going to things like central geo plants, you know, for their central plants, and adding a lot of renewables and offsetting, you know, all of their energy use with renewables over time. That operational line is going to do what we saw before. That's going to flatten out, right? And so it might be flat before that 11-year mark. So we may never see a payback in this type of study. So unless you do the study and you think about it, you're not able to make those smart decisions. So that's what I have in the world's quickest presentation. And John, I will stop sharing and let you go.
All right. Thank you very much, Heather. Try to see if I can get my screen going here. Let's see here. Oh, hang on a second.
I love that picture. That's awesome.
Thank you. Those are my 2 daughters visiting my other daughter. Okay, how about that?
That looks good.
Great. Okay. Okay. So thank you both. So quick intro. My name is John Hyde. I'm the Senior Sustainability Manager at Chapman Construction. And I'm going to focus on, I have a project, a little bit of a case study, and I'll focus on some things that we implemented in the field to achieve the desired high performance building. And also talk a little bit about the embodied carbon of that building. These are the learning objectives, which we've already gone through. And again, I'll hit on some of those focus topics from the Designing for Energy framework as we run through this. Just to set a little bit of some context for where this presentation is coming from. Chapman is we're an open shop GC. We do work in Newton, and we have an office we have an office in Manchester, New Hampshire, and an office in Newton, Mass. And so our project's a little bit smaller than the ones that Heather was talking about, and so I'll focus in on one of these. And but yeah, we have about 90 employees, 25 projects going on at any point in time. And we've committed to going carbon neutral by 2030, scopes 1 and 2. And so right now we're using our building as an experiment to rehab an existing building while it's occupied, and to go with, get rid of our fossil fuels and go all electric. So the case study that I picked, this is a project we built for the Southeast Land Trust up in Epping, New Hampshire. And this project is, it's about 8,000 square feet. It was on a existing site. And the client was looking for a highly energy efficient building. And they wanted to be able to invite the public in for nature-based engagement programs, and they also used it as office space. And it also connected them to a series of trails out back. They have 1,000 acres, so they want to be able to walk out of this building and access those trails. And then it's also going to be a place where the local community can grow food. So it's going to be a working farm as well. So for our project energy goals, we had some early meetings to talk about energy goals and also strategies for the project. And their focus is on the environment, and they made it clear that they wanted to rely on renewable energy and operate as much as possible in a pollution-free manner, and if possible, get to net zero on an annual basis. Our first objective was to get there, our first objective was obviously to reduce the energy demand of the building. So we focused a lot on insulation strategies, air sealing, windows and doors. I'll get into each of these as we go through the presentation. And HVAC, we looked at the air source heat pumps with heat recovery. And then we looked hard at lighting loads. We've got vacancy sensors, dimming, and we maximized the daylighting and incorporated some shades to minimize our lighting loads. And we wanted to make sure that we were definitely going to be net zero on energy on an annual basis. So we slightly over designed the solar PV so that we could export any extra electricity to offset other grid emissions. So I'll get into some of the building details. Often these to reduce the operational carbon, we've got a lot of nice details on the drawings, and I'll relay some strategies that we use to get the details off the paper and coordinated with the subcontractors and ultimately installed in the field. So typically we do a lot of pre-construction work, and we find that's a good time to work with the design team to work through the details just to make sure that they actually are doable and they're efficient. And we select products that and make sure that the manufacturer's requirements comply with what we're trying to do on the project. And we like to get that done before the CDs are done, so we can get those incorporated in the drawings, and then also make sure that all subcontractors that are being awarded this work understand the details and price it accordingly. So on this project, we were hired for pre-construction, and typically one of the first things that we do is so the air barrier is a big one for us. So we do we basically call it a red line review, where we draw a line continuously around the building and pay attention to anywhere where the line changes directions. Typically, wherever it changes a direction, that's a critical detail. Either geometrically, it's changing directions, or it's going from one material to the other. So those are the details that we pay attention to. And as we're going around, we look at as we're going around, we look at the line and make sure there aren't any thermal bridges as we're going across as well. We want to make sure we have continuous insulation, no thermal bridges, and continuous air seal. And while we're doing that, we will highlight the areas where we think there might be some where we need to pay particular attention, and we'll decide that we need to do a mock-up in those locations. And you can see some colors in the middle there. Typically, we color code them by trade so that they understand, what their scope is, and also if they need to come back, maybe they need to have multiple mobilizations, so they can include that in their the contract. If they have to go out, prep an opening, another sub comes out, does something, and they have to come back. So ideally, this is totally vetted and understood before we go out onto the job site, so that there's no surprises and the job moves at a pretty good pace. And also, during construction, we look at, we didn't really talk about this, but A4 and A5 emissions. What can we do to reduce our carbon emissions from the actual installation and construction process, and develop a plan and coordinate that as well with the subs, so that once construction's underway, we can try to reduce the A4, really A5 carbon. So starting on the bottom of the building, this is just a picture of a slab, pretty typical. We've chosen to just go 10 mil vapor barrier pretty much all the time. All seams fully taped and penetrations fully sealed. And this project has about an R20 under slab insulation. And oops, you probably see my mouse bumping around there. So again, we marked up the detail just to coordinate, how's the vapor barrier going to get installed and how in relationship to the sequence of the work and also the insulation. So you can see on the right-hand side, we've got the vapor barrier flopped over the foundation wall, left a little bit long, and then there's the slab edge insulation there so that once the exterior walls are set in place, we can connect that vapor barrier up to the outside of the zip and then come back down over the top of it for a continuous barrier. And then we do have some basement space. So again, on the left side there, you see, I'm not sure how well you can see these details, but putting a capillary break on top of the footing so that the, to stop the water from coming up into that foundation wall as much as possible. Again, so the details, just going through the details, blowing them up, color coding them, and understanding the sequencing so that we can make sure that's installed in the field. It's going to work and meet all the assumptions that we made during the energy modeling process. This project, again, thinking about operational carbon and embodied carbon, we used a double stud wood frame, light wood framing wall with blown in insulation. We decided to prefabricate the exterior walls off-site, and which turned out it didn't save us much time. A building of this size, the wood framing goes pretty quickly, but we were able to, the building has less waste if you're in better quality control and it's being built inside in a controlled environment. So you do save a little bit of money and time on labor, but you do have an extra cost for a crane and erecting wall panels out on site. So generally, our wall was pretty straightforward. We had Intello smart barrier on the inside, which the vapor permeability changes in relationship to the humidity and the temperature so that you can avoid condensation happening on the inside of the wall and resulting in mold. On the top right, there's always a couple areas. We try to reduce the amount of spray foam that we're using on our projects because of the global warming potential of the blowing agents, and also they just have a much higher GWP than other insulations. But in some cases, we use them in particular around rim joist or area where it's tough to get up and properly seal and insulate them. So we did use some along the rim joists to provide a nice air seal and high insulation value. Windows. So if we were going to build a building with no windows, that'd be easy. It'd be nice and tight. And we put holes all over the building, as you all know. And something as simple as a window. It's important to make sure that you understand what materials you're going to use and then what the sequence of installation is. There's often many layers of material that are installed, and the window opening can shrink pretty quickly. So you always want to make sure that you've done a mock-up to make sure that you have enough tolerance for shimming and stuff to comply with the manufacturer's clearances around the window. So again, pretty typical detail here. You'll often see these on drawings. We just take pictures as we go. The tape the corners and then the sides, and we install our top or window stops. Tape the corners again, and then tape the sides. Install sealant, and then install the windows, and then tape the side of the jambs and the header in the window, and then leave the sill open for weeping. So generally, let's see what the next slide is here. Yeah, then the roof. So the same thing. We've got our nice airtight layer. It goes from the walls all the way up to the roof. We want it to be continuous. So we're always looking at that top plate to attic transition. How do we set our trusses? In this project, we use engineered wood trusses. And so we had to figure out how do we get that continuous air barrier from the outside up into the attic wood floor. So we had to add a little bit of plywood in there so that we had something to tape to as we came up over the top of the wall and back into the truss system. And I've got a couple of snapshots here down on the bottom right, probably tough to see, but the original design was we needed a place to put the air handlers, and instead of doing the trusses as designed in the bottom left here, we re-engineered the truss so that we could fit the mechanical equipment inside the conditioned envelope, and then had this little step up over the top so that we could dense pack cellulose insulate the attic. So we ended up going with a two-piecer, this main portion of the truss, and then a little triangular piece that got installed on the top. And then over on the right-hand side of the building, the roof that already has the membrane on top, that was a different system. We had a hard ceiling in there. We ended up going with polyiso on the roof and also some dense pack cellulose in there as well. So on average, the effective R value of the roof was about a 60. And looking at Heather's presentation now, I'm wondering if we could have gotten away with a little bit less, but oh well. Okay. So the mechanical system, pretty standard mechanical system. We went, since our heating loads are so small, we could go with a fully electric VRF system. We installed the branch circuit controller so that we can do simultaneously, or we can move heat around in the building. If one side needed heating and the other side needed cooling, we can move the heat from if one side is needed cooling, the other side needed heat, we can move the heat instead of creating it, increasing our coefficient of performance. We did install an ERV, and so we have continuous demand control ventilation. So we had CO2 sensors throughout the building. So we had continuous ventilation if needed. And we also installed some radiant ceiling panels in a few areas. A couple tough to get to areas. We installed ductless air conditioners. Got our heating and cooling loads listed there. And whenever possible, we're always big fans of full commissioning, whether it's a project of this size or a larger building. Any project we're doing, that's we typically advocate for full commissioning. To review the submittals, do some quality control out in the field, an extra pair of eyes just to look at things, and then also duct sealing and commissioning and everything else. We're big advocates of full commissioning. So this is a view from above. So we ended up going with a roof mount solar, and we also installed some ground mount arrays. And you can see our numbers. We are fully electric. There's no fossil fuels to the site. So on an annual basis, now we're overproducing energy. So we have about a 31.5 kilowatt hour export. This yellow building is also this was insulated and air sealed as well, the yellow building, and that's less than 0.6 ACH 50, so that's tight. But the occupants were not in that building for year one, so our energy usage, we're gonna have to go out at the end of this year and get some new numbers, but we anticipate that they're still gonna be energy positive. So while they're not knocking down their embodied carbon emissions, that extra solar is being exported off and offsetting some other grid emissions. So it's net positive. And we're finding that the all earth trackers there are, they're getting about 30% more solar production per square foot than the fixed panels on the roof. Blower door testing. So we own our own blower door testing equipment, and we'll do blower door testing at throughout construction just for quality control purposes. We'll always hire a third party to come in and do the test afterwards. But generally, we like to do it before the installation's up, certainly, and we do them as many as we can just to see where we have leaks and jump on them as soon as possible to make sure that they get sealed up. So you can see about a month before construction was complete, we're actually at a 0.59 ACH 50. The goal was 1. Code in New Hampshire is 3, and we were at 0.59. We were missing door sweeps and some other things, so we taped those closed for the test. We did a little bit more work, and when we went to our final test, we assumed that we would be less than the 0.59, and we actually had gone up, and our security vendor had gone through and drilled some holes in the frames and installed their equipment, and also we installed the real door sweeps instead of the tape. So unfortunately for us, we went in the opposite direction and went up a little bit over passive house air tightness, but the owner was happy with it. Again, the target we set was 1. So we still beat that, but we could have gone. We didn't do air seal. Air seal is another option that was used on that historic house, the yellow house, for some areas that were tough to get. We couldn't open up, or certain areas couldn't be opened up because of the historical details of the house. But so aero seal is used to get that house tight, but we did not use it on this building. So the total carbon of the building. So we looked at the total carbon of this building. So and converted it into a. We've got our own nutritional label that we produced, and so the total carbon of this, we figured a 60-year life cycle of this building. Hopefully, the building will be here more than 60 years. But for our estimating, we did the quantity and GWP method. So instead of doing a spend-based approach, which a lot of people use, we don't really think those are that accurate. So we have we take off the actual quantities and figure out the global warming potential for each material, and that's how we calculate the embodied carbon. So A1 through A3, we used EPDs and industry averages, and I got another slide where I can show you what we did. I think Heather referred to it as the dark arts for MEPs. I can show you how we arrived at a few things there. So what I was surprised, and actually we did not include a couple quick notes on this before I run through it. So we didn't include biogenic carbon. The theory is, at least the way I like to look at it, is if you're not doing mass timber and CLT, that may end up getting reused in the future when the building's deconstructed. Most likely, if you're using light wood construction and things like cellulose, those are going to end up either getting burned or going to a landfill with the majority of those, with the majority of the carbon getting released back into the atmosphere. So we are not including biogenic carbon storage. Again, this is a full life cycle. If we were going to do an A1 through A5, we could have included some biogenic storage, but since this is 60 years, we did not. We also didn't include site work and then miscellaneous specialties for the building. Let's see, and we didn't include future renovations or upgrading mechanical systems or refrigerant leaks over the years, which is something that's important to consider, but it's a little difficult when you're not owning the building. You don't know when it'll be renovated and how the building will be used. Ultimately, there should be some B and C stage emissions added in here, but for this example, we did not include them. And then also the solar electricity in New Hampshire is much greener than it is down here. 50% of their emissions are offset because we're using nuclear and hydropower. So there's a grid factor of 0.105, which I used in this on the right. If you look at the export, so you can see as the years go on, the bottom blue, it's not showing. Oh, yeah, you can see it's negative. So when you get to mid 2040s, you can see that their grid is getting greener and greener and greener as we go. And so by the time we get to 2050, they're exporting electricity. But if the grid has no emissions at that point, then you're not really going to be offsetting any more emissions for New Hampshire. What I found interesting about the chart on the right is how high the HVAC emissions were. Again, there's not a lot of data for MEPs. I know people are trying to request them, but the manufacturers just haven't produced them yet. So we, but HVAC equipment is sheet metal, copper, aluminum. So it's all really high embodied carbon material, a lot of manufacturing, a lot of shipping of parts around to have it built. It's almost double what concrete is. So for our building, we had 440,000 kilograms of CO2e, which in the first year is about 200 metric tons. And after 60 years, taking into account the offset carbon emissions on the grid, it brought it to about 184, which equals about 0.394 kilograms of CO2 per square foot per year. And then down at the bottom there, you can see I just crunched some numbers for our EOI, and also just put our air leakage results on there as well. So we're trying to put these on all of our projects moving forward, so that we can start having some historical data to compare them to. This is how we do it in our shop here. We've got quantity takeoffs. We're using Procore. We're already to do our quantity takeoffs. We're already doing that to calculate our unit cost. So we find that calculating embodied carbon pairs nicely with that. That's done at the same time. So you can see down on the bottom right, you got a unit cost times a quantity. That gives you the cost for the material. And if you extend that quantity times the unit kilogram of CO2e that we pull from various sources, you get the kilograms of CO2e. What that does is that shows you within these sections what has the highest embodied carbon. So what can you focus on? If you want to reduce your embodied carbon, you would want to focus on these carpet squares because they're the majority of it. And so industry challenges with this stuff. So there's very limited data when it comes to specialties. Site work's highly variable. It's very much dependent upon the job site, where it's located, how idle time, ledge, things like that. So it's tough to calculate the A5 emissions for site work. Also MEP. So we started trying to create our own values for MEPs. You can see in the middle there, that's meant to be a water heater. When we were figuring out one day what is a water heater made of? Insulation, metal, glass, copper. And so we figured out the weights and put some used published values for materials, and then applied a manufacturing percentage to that to come up with the values that we used for our global warming potential. Also, there's a lot of new materials out there, low embodied carbon materials, but a lot of them aren't regionally available. So we got to get the EPDs on that stuff as it pops up, like Timber Lab or Timber HP up in Maine just opened up. They have dense packed cellulose and board insulation. So it'll be important to take a look at the EPDs on that to see if that stuff is much better than the Gutex that was getting shipped from overseas, so that we can use those. Also, a big void is the deconstruction of a project. The disposals on recycling markets right now are not where they need to be. There's storage area is at a premium for cost a lot of money to own a warehouse just to store materials here in Eastern Massachusetts. So I think there's going to be some markets opening up in the near future to be able to address and make more of a circular economy for some of these materials that are getting demoed and are still a lot of life left in them. One more slide here. So during construction, we've been trying to collect as much data as we can. For right now, RMI suggests using 6 to 12% for A4 and A5 emissions. We're using 10 temporarily until we get some more data. But what this chart shows here is we crunched the numbers for traveling for 21 days for a month, and it accumulates to be a huge amount of emissions when you tally it up. We took the average distance traveled times the number of workers. So as you can see, it's and then we just divided it up in a different a couple different metrics. This way we can extrapolate and use this data for future jobs. If we have a job that's going to last 12 months, we've got square foot per month here, so we can extrapolate this times the square foot of the building and the duration of the project to give us a starting point anyway for CO2 from travel. We're starting to collect as-built quantities for all of our materials and monitoring our electricity usage and fuel use as well for equipment, temp heat, generators, everything. Restricting idle time of equipment, trying to schedule deliveries so that there aren't trucks backed up. And then if possible, some belts starting to have hybrid generators that are available for so you can charge a battery instead of running a generator for the whole day and only charging a couple tools. You could use a generator to charge a battery and then run that battery to make sure that you're using 100% of the power. We're getting short on time. Last slide. So again, just a lot of synergies here when you're going with these low energy buildings. You have excellent indoor and outdoor air quality. You're not burning fossil fuels on site, so you have nice clean air outside. The buildings are durable, they're comfortable. You know, this building, when you're inside, feels great. There's no drafts. The air quality is great. We harvested a bunch of ash from the site. Is where the and we used, you can see in the wall there, that's all ash. We used ash for the stair treads, wall paneling, some ceilings. So in addition, we're supporting local economy using materials from on site, and you know, it's bringing the nature right into the building is great for mental health. And then you have the connection to the outdoors, so you can just walk right out the door, off the deck, and out on the trails. So that is it from me. I think we will go back to Patrick, who might be tending to the slides or the chat session here. So,
all right. Thank you, Heather and John. It doesn't look like we received any questions in the chat, but I want to invite everyone that is still with us to chime in. You're welcome to either come off of mute and ask your questions directly. You're also welcome to put your questions in the chat, and Beth and I will moderate the discussion. One of the things that, to start things off, one of the things that I think, you know, the AIA framework is really trying to kind of democratize the approach to reducing energy on projects, make it more realistic or tangible, is by focusing on, you know, what are the most important or impactful things that we can do, you know, to keep it simple, but what's the most impactful thing that we can do? So I'll pose this question both to John and to Heather based on the work that you're doing and some of the content in your presentation. If you could name one or two things that you think are the most impactful things that, you know, designers can do to reduce energy and to reduce carbon on their projects, what are those? So let's start with Heather.
My first answer isn't really helpful, or it's very helpful, it depends. Ask the questions, right? Don't assume that this project has the same answers as the last project you worked on. You know, that might not be the same if you're doing, you know, a campus and, you know, the same cookie cutter building going on, but buildings are different, things change, technologies change, right? So we need to ask the questions and understand how our buildings are going to work and the materials that go into them. And then electrify, right? You know, electrify to the greatest extent that's reasonable to your project. But don't necessarily, but pay attention to it, right? Make the smart, right decisions as you're pushing, you know, technologies. Don't always go to the state of the art technology. A lot of times, state of the shelf is your answer. It is going to give you, you know, your lowest carbon solution for an everyday project. That's not every project, but that's a lot of projects.
Okay, thanks, Heather. John?
I'd say, well, you know, some low-hanging fruit is to, you know, advocate for reuse of existing buildings. You know, there's often, we celebrate a lot of new buildings, you mentioned this earlier, a lot of buildings with glass, you know, they're shiny, they look great, but, you know, they're terrible. So I think, like, you know, advocating for simple geometry buildings, simplifying the construction, and highlighting, you know, as many natural elements as possible. It's not always great for a big tall building. And then just speak up and advocate during the beginning of a design meeting. Push for this stuff. It'll often just you know, people just continue to have the same old conversations, but it's important to, you know, talk, you know, right from the start. Just bring these things up. You know, do you have any embodied carbon goals? Do you understand what embodied carbon is? Because often people will just shoot right past it and not understand you know, the impact of it. I know that a lot of people on this call are probably well aware of the impact of embodied carbon, but I bet if you get outside of this group and talk, there are a lot of people that haven't even thought about it yet. So they're still getting their head wrapped around the operational carbon and the new, you know, building codes. So I think it's having a conversation out of the gate and explaining to them how important this is.
Thanks both. We have a question in the chat. Has anyone started to incorporate audiovisual equipment into these calculations, assuming this is still a dark art similar to MEP? I'll speak for myself. So one of the things, it doesn't come up all the time, but it has come up more lately, has and this is more of an operational than an embodied carbon answer, but is the use of large display screens that are always on, maybe in like a public area, a lobby, things like that. We see them more commonly in, let's say, academic, commercial, like public spaces, like lobbies, things like that. And these can be both like large actual screens, but also like walls, video walls, things like that. And as we're trying to substantially reduce the energy consumption within our buildings through improved envelope and energy recovery and efficient MEP systems, these video walls have a disproportionately high impact, both in terms of the actual energy draw, just to illuminate the thing, but also the heat that they're generating, and thus the impact it has on the HVAC system, are substantial. We have a project that recently opened where it was designed for net zero. It was a lab project and had a lab designed for an EUI of, let's say, 51, 52. And adding one of these screens, which was on the order of like a 10-foot by 12-foot video wall, had like a 10% total building impact on the EUI of the building. So, those are the types of questions or conversations that we have with whomever is bringing this idea to us. It looks cool. It, is an opportunity to provide branding or whatever, but these things are always on. They're very bright. They're very energy intensive. They produce a lot of heat. And so are there other ways that you can achieve your goal, maybe a little bit more subtly, or do you need it to be 10 by 12? Could it be 6 by 8 or things like that? The ways that you can kind of optimize this, especially on these projects that are more ambitious about net zero, especially some AV equipment can kind of shoot ourselves in the foot from an operational carbon perspective. But I'll open it up. I think Heather has been nodding vigorously because she's seeing it too on projects. So what's your perspective?
No, yeah, I mean that's a super great point. As our buildings EUIs go down, everything matters more that we used to not think about, right? And that's kitchen equipment, that's audiovisual equipment, that's occupant plug load, right? That's everything. It all starts mattering more and more and more. And you can't get to zero without occupant behavior. I will say that I think it is a dark art from a kind of embodied standpoint, embodied operational. And I start thinking about audiovisual in kind of a similar way, where I think about interiors where they're understood or underappreciated for their long-term impact, because the cycle they operate on is really quick. So they have a lot of weird special materials, metals that have a lot of embodied carbon in them, and then you're replacing them every 5 to 10 years. So on a 60-year lifespan of a building, you might replace that 12 times. By then we'll be running computers off potatoes, but it's that repetitive thing. MEP systems, interiors, start showing more impact than we've given them credit for previously.
Yeah, I don't really have anything to add. That was well said. When I just was budgeting putting together an embodied carbon budget for a clinical a lab building for an institution, a clinical skills lab, and there's six of them all with these big displays. And for the embodied carbon, I just kind of looked around at some different things and came up with my own numbers for those. But you're right, Heather, on the cycling of those, like bulbs burning out and they're always on. There's you know, it's a high embodied carbon impact, and the life cycle is definitely not 20 years like a lot of other things are. You know, the EPDs that come out will often list the life cycles, and I think when you're looking at the EPDs and what the manufacturer is suggesting, you know, take a look and you read those things closely, and you know they still have a like plus or minus 40% on them, so it's a huge swing. So just be careful and look at more than one when you're trying to make a selection, and just try to use some common sense when you're looking at the data sheets or the declaration sheets to make sure that you're understanding what they're reporting on. They're often a little tough to figure out sometimes. Yeah, look at the declared unit.
I will say the flip side of everything that we just said. So we have an office building in design right now, a large new office building, fully fit out in the scope, which admittedly are not that common in this economy these days. And it's subject to the new Massachusetts laws, energy code, and needs to be all electric and super efficient. And this project has a data center within it. And so we're actually, you know, taking what is otherwise a negative thing from an energy perspective, this relatively energy dense space, and we're turning it into an asset for our project. And by capturing the heat rejection from that data center as the primary source of heat for our building, perhaps even for the building next door, we're electrifying the building without even needing to use external sources of heat, whether it's an air source heat pump or ground source heat pump or whatever. So we're doing a substantial amount of that work by leveraging that heat, you know, that we have within the building. So there are opportunities there, but you have to be deliberate about them, and it needs to be the type of conversation they're having at the very beginning of the project. All right.
Yeah, you should never let any of the heat that's in your building leave without taking full advantage of it. You paid for it, you should use it.
Yeah. All right. Are there any other questions from the audience? All right, so George typed in, can someone from the panel comment on whether there is forecast availability of power from utilities to support building and vehicle electrification, albeit with lower energy intensities? I have my thoughts on that, but Heather, do you want to try that?
I can't speak definitively to that. I will say that it's a really popular, it's a topic that we need to be thinking about. There are, you know, it's a chicken and egg thing too, right? We're creating demand, and at the same time we're building supply. And you know, if we wait till we have full supply, we won't create the demand, so we won't build the supply. You know, we don't build infrastructure in this country that we don't need. We build infrastructure when we need it. And, you know, I don't think this is any different. It is a concern, but I think that's my opinion.
Yeah, I think, you know, the utilities are operating on a different timeline in the building. When we're building a building, you know, we're talking 3 years, you know, from planning and building a building or whatever. And they're operating on a 6 or 7 year timeline for bringing, you know, big major infrastructure upgrades. And they don't really know at this point where they're going to go. You know, so they're thinking about building upgrades. They're also thinking about, you know, the side of the pike where you now need to be able to charge, you know, a bunch of trucks and cars and everything else all at the same time. So they're bringing like a feeder the size, you know, that would be what you would need to power a small city to a rest area on the side of the highway to be able to allow enough vehicle charging. So it's a struggle. You know, it'll be interesting to see how it all plays out. But I know ISO New England has reports that they've published that you can go in, you can look, and you can see how they plan the energy transition as fossil fuel plants go offline and renewables come online, and how they plan on getting power to all these different areas and prioritizing different locations. Pretty interesting. Good read.
All right, thank you both. So we're coming up at the end of time. I'm gonna repost in the chat for anyone that hasn't already done this, If you are looking for recording your continuing education credit for participation, for those of you that are live attendees, please fill out the link that I just put in the chat, and the BSA will complete that for you. And if you are looking for a certificate, I believe they'll provide that as well. And I'll hand it back over to Beth.
Awesome. That was my only announcement, Patrick. So thank you so much. And thank you, Patrick and John and Heather. This was amazing. I want to remind everyone that if you need a refresher, that this will be posted on the BSA website. And also please join us January 17th for Design for Ecosystems. Thank you everyone for joining.
Thank you.
Thank you.
Yeah, bye.